Hello boys and girls, it is Mr. Malzberger here. We are about to have our final lesson in exponents and roots, Unit 7, lesson number 6. Okay, so today we are going to talk about scientific notation. Scientific notation is just a pattern that happens with really big numbers. It's used by scientists, obviously. That's why it's called scientific. For writing really large numbers and really small numbers, which are very long, in a shorthand, so they fit into a book. For example, if I wrote 43 with all these zeros after it, right? So that's a lot of zeros. And if I wrote that into a textbook, especially one that was formatted where it had two different columns or something like that, that would take multiple lines and be kind of hard to look at. So what they do is they use the base 10. So, for example, 4 times, let's say, 100,000, right, is 400,000. You can write this as 10 to the power of, there's 1, 2, 3, 4, 5 zeros. Just the power of 5. Because 10 to the power of 1 is 10, 10 to the power of 2 is 100, power of 3 is 1,000, power of 4 is 10,000, power of 5 is 100,000. So what this really is doing is taking the number 400,000 and writing it like this, and they usually put an X right here instead of a dot. It's 4 times 10 to the power of 5. Now this one right here is much larger. Now there is a format that they follow, and they find the first real non-zero number, and that's going to be in the ones place. Always the ones place. No tens, no hundreds, no thousands. This goes in the 1. And so then there's always a decimal that follows it. And all the other non-zero numbers are listed. There's only a 3 here, so it'd be 4.3, right? And then we're going to say, well, it's times 10, and then we just count how many spots the decimal has to move. Now realize the decimal is right here, right after the 4. So we're going to count by 3s, 3, 6, 9, 12, 15, 18. But 18 only gets us to this part right here, before the 3. So one more, 19 gets us right there. So 4.3 times 10 to the 19th power is a lot easier to put into a textbook than this number. And really one of the main reasons that the scientific notation exists is because you can't put some of these numbers into a calculator and have them register them correctly. So you have to put in a shorthand for them to work. And that's why we get answers for giant numbers in this format. I'm sure you've seen it before. So let's do a couple practice ones, just for fun. Just for fun, I say. And you look at me crazy because you say, it's math, Mr. Malzberger. How can it be fun? It's just a silly pattern. You really don't even use these that much. They're just used for writing. So it's just understanding how to transfer big numbers into scientific notation form and then back out. Because if we're ever going to use these numbers, we're going to use them like this in a calculator, or if we want to write them out to see how big they really are, we do that. And I'm not even counting. I'm just throwing zeros out here at random. Okay, so you have a giant number, right? Whereas the first non-zero, it's 5. So it's going to be 5 point, list all the non-zero numbers that follow, 8. Okay? Now, everything else is 0, so we're going to do times 10. And then we just count the zeros, 3, 6, 9, 12, 15, 18, 19, 20, right? That's all my zeros. There's 20 zeros. But I have to get all the way to here. So 20, 21, 22, 23. You're counting how many spaces, right? That's what scientific notation is. We're just writing this big old number in a shorthand form. Why would anyone have to use this, right? Well, I'll give you a real life example here that we can look at to practice. The distance in miles from Earth, good old chunk of dirt and water, Earth to Alpha Centauri. If you do not know what Alpha Centauri is, it is our nearest solar system. It's the closest one to us. How far away is it? Well, in miles, it is this far away. So, of course, you got your hundreds, thousands, millions, billions. It's 25 trillion miles away. It's like 4 point something light years in distance. So, in the textbook, if people wanted to list, they rarely list it in distance of miles. I had to go hunting for it so I could get a big number. They just list it in light years because scientists know how many miles are in a light year. But let's turn this into scientific notation. First number is 2, so it's going to be 2.567 times 10, because the rest are zeros, 369. And we're going all the way to here, which makes 12, and one more makes 13. Kaboom, right? There's a opposite of this, of course, is I give you a number in scientific notation form. Like if I gave you 7.92 times 10 to the 11th power. This is scientific notation. Let's make it expanded form. What's the real number? This is pretty simple. You're going to write this number, 7.92, and then you're going to move the decimal this many times to the right, 11 times. Now, for me, instead of doing the 1, 2, 3, 4, and doing all the little like loops and trying to then fill in the zeros, I find it's, especially for, what if I give you 21, it's easy to get the zeros wrong. So what I do is I count how many numbers are past the decimal. There's 2, and I take it away from the 11, because that's 2 decimal spaces right there. So 11 minus 2 is going to give me 9, which means I have 9 zeros following this. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the full number, and I'm leaving little gaps. I'm not sure if it should be like 3 from this side or that side. I'm just leaving gaps so we can count easier. So that's 11 total spaces. 3, 6, 9, 10, 11. Wait, what did I just do? Yeah, this turns into a comma, of course, with this one. Bink, 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 and that's why this is wrong. Do you see why it's wrong? Because I spaced it out wrong. So it should be 3. 1, 2, 3, comma. I was already thinking about small numbers. I'll explain that in a second. 6. That's those. There's 9. And then it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it's 2, 9, 7. Right? Okay. So sorry, I did that one weird. You're probably like Malzberger. When I get to negative exponents, you'll understand what I did there. I actually just flipped it in my brain. Here's a real one for you. Hurricane Sandy cost the United States this much money. How much money did Hurricane Sandy cost us? Well, I'm going to take the 6.5, and that's 1 decimal space. So how many zeros go after? 10 minus 1 is 9, so 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 in comma, 3 in comma, 3 in comma. It costs us 65 thousands, millions, billions, $65 billion for Hurricane Sandy. So we can make big numbers into small numbers in a truncated shorthand, and then we can expand and make them big again. And also in science, we have giant numbers like the distances in space. And we have tiny numbers like this. Okay? This is a tiny number. How many inches are there between two atoms? I don't know. This is just a random number. I'll give you a real one in a second here so you can see it. These numbers are written just like these. They follow the same pattern, but since we have a decimal here, these are tiny numbers. Big numbers have positive exponents. Tiny numbers are going to have what? You said it. It's going to be negative exponents. Because remember, a negative exponent, so if I have 10 to the power of negative 3, that's really 1 over 1,000. So that divides the number and makes decimals, right? So if I did that times 8.7, I would have my decimal moved over 3 spots. Or 1, 2, yeah. So right there's my decimal, right? This makes a small number. That's what these are doing. Here's how you do it scientific notation wise. Find the first non-zero, 8. Put the decimal. All the other non-zeros go after. And this is the easier one because it always ends. They never put zeros after it. So you just write first number, dot, whatever follows. Now let's count how many decimal spaces it moved. It moved to right here. So there's 3, 6, 9, one more makes 10. So instead of positive 10, it's now negative. Tiny numbers are negative numbers. Positive exponents are big numbers, right? Here, I'll give you one to try right here. I'll squish it in. 0.000000246. Want to try it? Okay, here we go. 2 is my first number, so it's going to be 2.46. It's going to be times 10, always times 10. Now I've got to get my exponent. There's 3 there. 3, 4, oh. I said that weird. 3 and 3, and then I said 4. 3, 6, 7, 8. So negative 8. And that's all this is. It's a pattern, right? If I gave you the opposite, if I gave you 7.26 times 10 to the negative, let's say 12. How do we expand that? Well, I've got a pretty easy trick. All you do is make this many zeros. Don't make spaces. We'll put commas in even though they look weird. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Write this number. Now, there's a decimal. It has to go after the first 0. So what you'll see is there's a total of 3, 6, 9, 10, 11 zeros, right? There's 11 zeros here. To move one space to the left takes us 12 down to 11. So if you just write this number of zeros and put the period, the decimal point, after the first 0, it works every time. So here, let's try one just for fun. 8.47238 times 10 to the negative, let's say, 16. Well, how many do we have here? 1, 2, 3, 4, 5. Does it matter? No. All that matters is this. So let's make 16 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then put this number, 8, 4, 7, 2, 3, 8. Decimal point should be 15 zeros. 3, 6, 9, 12, 15. Kaboom. We're right. Now, before I give you the practice, I'm going to show you one example of where these numbers actually kind of are used. It's nothing you're ever going to deal with. But here is a number. And it's very big. Right? 3, 4, 5, 6. Okay. This number, and there's millions, billions, trillions, quadrillion, quintillions, I don't know, is it sextillions? I don't know. It's a big number. This is the number of carbon atoms in a 1-carat diamond. So if your mom or someone you know has a diamond ring, you say, hey, is that a carat? And they say, yeah, that's a 1-carat earring or ring. That's how many atoms of carbon it takes to build that. That's how tiny they are. Now let's write this in a much more reasonable way. So it's always the first number, 1 point, and we have to get all the non-zeros in. So I have to do the 0, 3 here, because I can't just do 1 times 10, because that 3 will get lost. So now everything else is 0, so it's going to be times 10, and then we got 3, 6, 9, 12, 15, 18, 3 more makes 21, 22nd power. This is how many carbon atoms are in a 1-carat diamond. Now, this is how much one carbon atom weighs in grams. Four, five, six, 7 of these, right? 1, 2, 3, 4, 5, 6, 7, 020 grams. This is the weight, the mass of one carbon atom. It's a tiny, tiny thing. So to write this one, you'd put the 2, and you could do 0.0 if you wanted, or just 2, times 10 to the negative 3, 6, 9, 12, 15, 18, 21, 22, 23. You see how this number is just really hard to look at? It is. But these numbers are, okay, scientists would know what this is because they work with it. We don't work with it. But they would know exactly how big this is and how to deal with it. But we can use these on calculators. Here's some real life examples of it. Will you ever use it? No, but you will see it in your science textbooks as you move up in grades. So let's do your practice. You have 4 that I want you to put into scientific notation, and then 4 that I want you to expand on. So pause the video, get those done, and let's check them. Ready? Here we go. All right, so big number first, number 1. So I'm going to put the first non-zero number, 2 point, followed by 3 and a 4. And it's times 10. Count the zeros. 3, 6, 9, 12. And I got to move it all the way to here. So there's 15, and one more makes 16. Right? Because we got to get the decimal to right there after the 2. Number 2, 4. Point, got to get all 3 of those, 0, 9, 3, times 10. I'm moving it right to here. That's easy because it's groups of 3. 3, 6, 9, 12, 15, 18. Okay. Number 3, we're making negative powered ones. So there's my first non-zero. So it's going to be 2.367 times 10 to the negative. There's 3, 6, 9, 10, 11, 12, because it's got to go right there. Boom. Again, first non-zero for number 4 is 9, and that's 0.46. It's going to be times 3, 6, 9, 12, 15, 16, 17. Negative 17th power. All right. Now we're going to expand. So for 5, we got a big number. So remember what I do is I count how many numbers are past the decimal, 2. I'm going to subtract it from the power of 9 to make it 7. So I'm going to do 1, 4, 5 with 7 zeros. 3, 4, 5, 6, 7. Go backwards by 3s and insert your commas, and we've got 1,450,000,000. Right here, I've got 1, 2, 3, 4 numbers past the decimal. So 15 minus 4 is 11. So I'm going to do 7, 2, 7, 5, 2 with 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Go back by 3s. 3, 3, 3, and 3. So we've got millions, billions, trillions, 7 quadrillions, 275 trillion, 200 billion. That's a big number. And now let's make some tiny numbers. Remember, I'm going to take the entire exponent, make that many zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, followed by all the non-zero numbers, the 4, 8, 9, 5. The decimal goes after the first zero. I should have 10, 3, 6, 9. If I wanted to put commas in, I could to make it easier to look at. I don't even know what this number is, because there's the thousands, 10, 100, millions, billions, trillions. Yeah, I guess. I don't know how you even read this number. It's beyond my memory. Anyways, moving to the last one. Sorry to waste your time. Here we go. We're going to do 14 zeros. My God, why did I make it so long? I must not like you guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm going to put one more here. 14 with a little bit of a space. 2, 7, because I realized I crammed that together and couldn't fit a decimal in. So there you go. There's 3, 6, 9, 12, 13 zeros. And that is your practice. Hope that was easy. This is your last lesson of the unit. We'll have a review and a test next week. Hope you're doing great.